Hello, my name is Brian Moda, and today I will be doing a combined loading problem. I'll set up my DocuCam. So for a beam system shown loaded below, find the principal stresses and max shear stresses at point H. All three sections are solid cinders with diameter of 5 centimeters. So what we want to do is we want to combine all of our loads, our load forces, to be in one single um, one single reaction forces and reaction moments. So all of these forces create a reaction to each one. So we all want to simplify and we want it one. And after we do that, we need to use that information to plug it into Mohr circle, and we can find our principal stresses and max shearing stresses. So with that being said, what we want to do is, first off, we want to simplify it to have our reactions at X, Y, Z, moments at X, Y, and Z. So what I do is I have a load, and at that load, so each of the loads, we have 50 kilonewtons, we have 9 kilonewtons, 13, and 17. So here we have our R, we have our F, force, and then our M. So this is my moment, these are my forces, and R is the distance from point of interest. So I have my components I, J, K, I, J, K, J, K. So for my 50, let me highlight the forces, that way it'll be easier to identify. We have 4, so for our 50 Newton or 50 kilonewton force, that one is at the center. So we have our distance is 0. We have 6 meters, 0. And then for our 9 kilonewton load, we have 0, we have 4 meters, and then we have 2.5 going out. For 13, it's the same, so 0, 4, 2.5. Our 17, we have 1.5 meters, 6, and 0. So for our F, it's just all these values, just here. We just have to pay attention to the rotation. It's going down, so it's 50, 0. Then we have 9, positive 9, 0, 0, 0, negative 15, 0. And then for 17 is 0, negative 17, 0. So for our moment, it's just cross product between these two. And if we do that, we end up getting 0, 0, 0. For our 9 kilonewton, we get 0. We get positive 2, 2.5. For our K, we get a negative 36. For 13 kilonewton, we get 32.5. We get 0 and 0. For 17 kilo, we get 0, 0, and negative 25.5. With this, when we find our reaction X, reaction Y, reaction Z. We also want our moment X, moment Y, moment Z. How we calculate this is we go down the row. So our I's is our X. We go down, we add all of them. So actually we add them and then we do the opposite sign because our reaction of here is the opposite. So this is -9. This is, you add all of these three and you get -80, but you want the opposite sign, 80. And then for z is 0. And then for your moment, you add them, so you get -32.5. Here you get -22.5. And then if you add these two, you get a positive 61.5. So with that being said, when we have a combined loading problem, our first step is we want to have a transverse cut at our point of interest. Before I do that, I want to explain, before I go into that, I just want to explain what an axial load is and a transverse shear. So what it is, basically, this helped me a lot. So the axial load is going into, so it's going in, and then transverse going perpendicular. So this is axial, this is transverse. So an axial load is defined as the force of structure going directly along the axis of the structure, and then transverse is just perpendicular to that. So this information is gonna help me later in those next steps. But also, if we, so our view right here, say we have the end view, which we're looking at it at the bottom, so we're gonna have a circle. Say if I rotate it a little bit and I put my H at the, this is my H at the top, I'm left with my axes of Z and then X that way. So with this, I know that my neutral axis is going to be here, and then this area right here is going to be my Q. And we know that in order for there to be a neutral axis, both of our areas on both sides have to equal to each other. Another thing with our shear stresses, when you draw the cut, it looks like this, and then you have that. So our neutral axis is here, and I know I'm going to explain later why I know that's my neutral axis. So if you have a stress here, it's gonna look like a parabola. This is our tau distribution, so our shear stress. So it looks like parabola, and as Q, so if Q is approaching here, it increases to the center of the parabola. And I know the shape looks like this because at page 375 in the textbook, it proves this. So with this being said, I'm gonna solve for my reaction. So for Rx, I know this is a transverse. This is a transverse shear. What helped me is by looking at this problem. So I'm going to explain why. So if I have the same view, this view, let's say I have the same view right here. I have my Z, I have my X, and I'm going to make it look kind of 3D. So let's say my tube is like this instead of vertically seeing it. And then my Y is going this way. So at this point right here, it's on my neutral axis. So there's no moment, which is 0. And then here, the best way I can describe it is with this eraser. So say it's kind of looking like this. So if I have a moment going downward, it's gonna look like that. It's gonna go up and down, which means it's gonna be bending. So if I have my Y right here and it's going this way, then I know this is gonna cause like this, and it's gonna cause to shear. It's gonna cause torsion. So it's gonna look like this. This is torsion. So here at my Y, I know there's gonna be torsion. And then here, this one, I know there's gonna be bending. So this is my X. So I know at my RX, my reaction, there is a transverse shear because this is my axial. Right here is my axial load, or actually, so if I look at it right here, like this, my axial load is on the Y. So my point is right here, is on this. So my axial passes through that point. So this is my Y. So my reactions is the opposite side. So it's gonna look like the opposite. Here, this is gonna be my axial. And then these two are perpendicular. So I know this is transverse. It's axial, transverse, torsion, and bending. So for my RX, I know this is my cut. My transverse cut looks like this. Because if I have it like this, the picture, here, I'll put it right here. So if I have it like this, say I flip it, I go like that, and I have it like this. So my Y is pointing inward that way, and then my my Z is pointing upward. So this is up, and then the Y is going in. So I'm just having this and I'm turning it this. So that is this view right here. So I'll have, actually, it's my X right here. So here, I'll just draw it. So X, and then inward is my Y, and at this point is my H. That is my transverse cut. So I know for my transverse shear stress, my bending, this is gonna cause bending. So my bending formula is tau equals VQ over IT. And to divide these terms, so my V is my shear force. Then my Q is the first moment of outward area. My I is moment of inertia, and T is my thickness of the beam at our point of interest. So I'm gonna solve for my I. So my inertia of a solid cylinder is 1/4 pi r to the power 4. And also at the same time, I'm gonna put Q. I'm gonna solve for my Q, which is my Y over A. And this is my distance from the neutral axis, and this is my area. So this is my cross-sectional area, this area. So after that, I'm gonna plug in. So if I plug in my values, I know the diameter is 5 centimeters. So 1/4 pi, my radius is gonna be 0.025 meters because I converted this. So my I equals Sorry, I'm gonna write it more up. My I equals 3.068 times 10 to the negative 7. And then my Q, if I plug in my Q, this equals 4r over 3 pi times 1/2, which is half of the circle, pi r squared, the area. So if I plug in, I get 4.025, 3 pi, 1/2 pi, and then my r is 0.025 squared, and then my Q is gonna equal 1.042 times 10 to the negative 5. And then my thickness equals 0.05 centimeters, or 0.5 meters. And my shear force, I know for my x direction, so my Rx, so V equals negative 9 kilonewtons. So if I plug this in, I'm gonna plug my equation in. I want to keep it in the same paper. So tau xy equals VQ, I rewrite it IT, which equals, if I plug this in, I get negative 9 kilonewtons times my Q, which is 1.042 times 10 to the negative 5th, over my I, which is 3.068 times 10 to the negative 7, times my thickness, which is 0.05. If I plug that in the calculator, I get negative 6113.4 kilopascals. And now, new paper. So now I need to write, or I need to draw my stress blocks. My stress blocks at Rx. So I need to draw like this. So this is Z, Y, Z, X, X, Y. So when this is a transverse shear, you have your blocks look like this. So you have this. Since this is negative, it's gonna go this direction. I'm just gonna go that. So I have 6113.4 kilopascals. That's the stress blocks at Rx. So now I'm gonna go into my moment X, so MX. And this is still bending. So this is bending instead of transverse. So at moment, it causes the beam to bend. So I have my equation equals, oh, first I gotta draw, well, here, sigma y equals my over I. So my transverse cut looks like this. So what I want my my MX, so my X to go into the page. So it's left me with my Y and here my Z. So if it's going into the page, my MX is gonna go this way. My MX is going that way. So if I plug in my values of my MY, which is right here, negative 22. So if I plug this in, I get my moment at my, I get negative, oh sorry, my moment at x, not y. So it's this one, negative 32.5. And then my y is my outermost fiber, so it's 0.025. My inertia, I calculated that before, and it was 3.068 times 10 to the negative 7. If I plug that into my calculator, I get 2.65 times 10 to the 6 kilopascals. So if I draw my stress blocks, so stress blocks, same thing. So just quickly, so y, z, z, x, x, y. So get that. So according to this picture right here, it's showing that so my beam, my x is going that way. So if it's going this way, it wants to go like that. So that means my, here with my eraser, it wants to go like that. So that is causing this to go down. This is my y is going that way, my z here, and then my x going that way. So it's gonna cause it to bend. So I know only my y is affected. So at my y, I know I got a negative value. So my negative means compression right here. So I also have a y here, so I have compression. So y at negative, it's compression. Well, it goes back to the elastic plastic model, which the elastic plastic model, just to be real short, looks like this. So at tension, you have a positive shear stress, is positive yield, and then right here it's negative yield, so negative. This is at compression. So that is what is happening right now. It's being compressed, that's why it's negative, and it's at the yield. So at the yield, it means it's the point where permanent deformation starts to occur. So that's why it's going inward. If it was tension, these arrows would go the other way. So those are the stress blocks. And now moving on to my RY axial. So my RY, it is an axial. It's an axial stress because of what I defined right here. It is going, so this is my point of interest right here. So it's going through it. So that means when it goes through it, that is my axial force, because it is going through my point of interest. So that being said, the equation, so my transverse cut looks like this. So this is my x, this is my y, and then my h block, this is h. So I also know here, you can see my point of interest and it's going through it. The equation for this is sigma y equals P. P is just the force, and then A is the area of the circle. So if I plug in my values, it is 80 for my RY. And then for my area, I just put pi r, which is 0.025 squared. And this leaves me with 40,000 743.6 kilopascals. And my stress blocks are gonna look like this. So same thing. Yep, you can see it. It's gonna look like this. So here I have positive. So that means I have tension. So this is gonna go outward. And then this one is gonna go outward as well. And so Z, Y, Z, X, X, Y. And my value, my value is 40743.6 kPascals. And I forgot to write my values, which is the same thing as 2.65 times 10 to the 6 kilopascals. I believe I forgot on the other side. Or yeah, I also forgot. No, I actually included it here. So I'm good there. Yeah, it's just the show. So I have to, since I have it on both, I have to write it on both. So 4743.6 kilopascals. And here 2.65 10 to the 6. That's just okay. So now that I have my RY axial, so now I have, I'm gonna solve my MY. So at my moment Y, I have torsion. I described that as my Y is going that way. So if I have a moment going around it, that means torsion is going to occur. So I actually drew it like this. So I have a circle, I have my Z, my X, and at the Z I have my H. So I have moment going this way, which is my MY. So the equation for this is my tau XY is gonna equal TP over J. So my T is just my torsion, which is my force. So this is gonna turn into negative 22.5. That is my MY right here. So it's 22.5. And then my P is just my distance from my point of interest, which is 0.025 meters, all that over J. So J is actually the polar moment of inertia. And a solid cylinder, this is actually described, so I'll just write, this is actually described as 1/2 pi r to the power 4. So if I plug in my values, it is pi over 2, and then my radius is 0.025 to the power of 4. So if I plug this into my calculator, I am left with a value of negative 91672.47 kilopascals. So I want to draw my my stress blocks. So this, like how we always been doing. So Z, Y, Z, X, X, Y, whoops, Y. And then, so torsion, how I picture this is, we want we gotta imagine this is elastic. So I'm going back to my transverse cuts here. Let me draw this bigger. This is my transverse cut right here. So to explain this is we have something that looks like this. When this happens, so these are arrows, by the way. So this is my neutral axis. And so at our neutral axis, nothing happens. So if I draw this, say like at my block would actually look like this. My block will look like this. And then say this is the neutral axis. Well, you know that this is gonna shift a little bit. This actually shifts like this, like that kind of. So this is actually gonna shift, neutral axis, nothing happens. So that's how I know my stress blocks. So at my Z, nothing is gonna occur. So at these two, nothing is gonna occur. So that leaves me with my XY. Since I have negative, it's gonna go in this orientation. And if it was positive, it'd go the opposite. The arrows would just flip. So I have 9.16 times 10 to the 5 kilopascals, which is this value right here. So now to find my RZ and my MY. My RZ is pretty easy. So I'm just gonna do this for note-taking purposes. So RZ is transverse, and it looked like this, right? So I have my Y and I have my X, and so if I had it like this, I know that I would have to solve it, and I'd have my moment. But according to the problem right here, our RZ is 0. So this equals 0. Now for our moment, so we don't have to worry about RZ. So I just did that for note-taking purposes. Now for my MZ, I know nothing occurs here because it is at the neutral axis. So as I was explaining with the other one, with the moment, so the pictures that I drew right here, at my neutral axis, say my neutral axis is Z in this case. So in this problem it is Z. So at my Z, my moment at Z, nothing is occurring because at here it is at the dead center. So literally nothing is happening. So my X and Y are affected, and that's why I also explained in the beginning that I knew my neutral axis was at Z. So with this being said, knowing all of the reactions and my moments, I can combine all my stress blocks, and that way I can plug it into my Moore's equation. So I can combine all stress blocks. So if I combine all my stress blocks, I am left with, oh, that was ugly. Anyways, this is Z, Y, Z, X. This is my X, Y. So how you combine all of them is literally, you go, say right here, you get your transverse, and you find another one an XY. So we just go through, and then we have another one here. So you just add both of them. But you have to pay attention to the signs. So you either have to add or subtract. Same with here. You do the same thing. You look at this. So say like right here, you have one in compression and you have one in tension. So you know you're going to subtract both of each other. And you do that with all the rows. You just go down. You go down. So this one, you don't have to do anything for my my XZ because I don't have anything there. For my ZY, I do have two, so I know this one is in compression, this one in tension. I have to add those two, which would in theory actually subtract from each other. So just to speed things up, I'll explain as I go, but if you add this one and this one, you know both of them, or this one and this one, they're both negative. So it's going to be negative plus negative, which is actually going to look the same in the orientation of the arrows. But if you add them, you actually get a value of 9.2. Oh, yeah. 9.2 times 10 to the 5 times 10 to the 5 kilopascals. And then say this one and this one, you're gonna this one's positive, so it's this one plus this number, which is a negative. If I do that, I actually get something that looks like this, going this. So since I don't have room, I'm just gonna write it here. So this is actually gonna be 26,1525.6 kilopascals. And if I go for this one, if I go down, I have nothing. So this one stays the same. Here I have nothing. We'll have these two. One is in tension, one is compression. So I'm gonna do this one plus minus this value. So if I do that, I actually get something that looks like this, which is in compression, which means my answer is in a negative. So it's 26,092,566 kilopascals. So now that I have all this information, I can use my Mohr circle now and find my principal stresses. So I'm not gonna go into depth about the Mohr circle, but pretty much it tells you your max principal stress that you can have and your max shear you can have at that application. So Mohr circle, using Mohr's circle, you get this. So my shear force, or my principal stress, and my shear 2. Yeah, so my shear stress 1 and my shear stress 2, that all equals my shear stress at X, because I'm using this one right here because it has all the information that I need. So I know it's my X and my Y. Say if it was this one or this one, then I would have used accordingly. It'd be X and Z or Z and Y. But in this case, I have that one. So it's my X plus Y over 2 plus or minus square root of sigma X minus sigma Y. And actually, cool note is that this right here is actually our max shear stress that from the equation. These are my max principal, and then this right here is my, or actually solving it. So I'll just keep going. So my principal stress 1, or I need to actually plug it in, so I need to show that. So my sigma 1, sigma 2 equals, if I plug in, I have nothing going through the x direction, so I have 0 plus, and I have a negative value because this is in compression right here, as you can tell. So it is negative 2.609 times 10 to the 6. I just same number, I just rounded it up. Sorry, 6.15. 6.15 times 10 to the negative times 2. So that plus or minus square root, and then I have my 0, which is my x value, minus minus 2.615 times 10 to the 6, 2 squared, plus, and then my tau is this value, my transverse shear. So it is 9.2 times 10 to the 5, 2. And I just need to verify some numbers because I had them flipped, and I just want to double check that everything checks off. So give me a second. So 2.615 and then 2.615 I get. So my sigma 1 is going to equal 291,291,235.8, and then this is kilopascals. So my sigma 2 is actually so this one's first value if I add them. Second value is if I subtract them. And that actually gives me a value of negative 2906,235.8 kilopascals. So to find my, so these are my two principal. Anyways, that is stress. And then this is my maximum shear stress, max shear stress. And then this is at point H. So my T max equals, so let me do that real quick. And that gives me a value of 1598735.8 kilopascals. And that is how you do it. So from here, if we actually had our like material, if it was like some type of, I don't know, copper or steel or whatever, if we knew that that information, then we would have checked if for failure. So we would have plugged this in back to our equation, and then we would have checked if it failed, and then if it didn't, then we'd have to tweak some stuff, or we would just say that it will break. But we don't have the information, And the problem is asking for our principal stresses and our max shear stress. So that is it. And this is my signature that I was the one that did it. And that's how you approach this problem. Thank you.